To solve this mathematically, we modeled the network as a graph. A graph is simply a collection of points, called vertices, and the connecting lines between them, called edges. In the real world, connections are rarely equal. Laying pipe through a mountain costs more than laying it across a flat plain. We represent this variance by assigning a numerical cost, or weight, to every edge. This creates what we call a weighted graph. If we want to link every vertex together without wasting resources on redundant loops, we must extract a spanning tree. A spanning tree is a specific subset of edges that touches every vertex in the graph, but never forms a closed cycle. As you can see in this model, a single graph can contain multiple valid spanning trees, each with a completely different total cost, depending on the specific edges we choose to activate. The exact configuration that connects all vertices for the absolute lowest possible total weight is called the minimum spanning tree, or MST. Finding this precise optimal path in a massive network is impossible to do by manually testing millions of combinations. Instead, we rely on a mathematical tool explicitly designed to locate the MST automatically, Prim's algorithm. Prim's algorithm is one of the definitive programmatic methods for calculating a minimum spanning tree. In computer science taxonomy, we classify prims as a greedy algorithm. A greedy algorithm operates on a specific logic. At every single step of its execution, it evaluates its immediate options and chooses the absolute lowest cost path available right in that moment. It never looks ahead to analyze the broader network. It never calculates global averages in advance, and it never reverses a decision once it makes one. To build the spanning tree, Prim's algorithm starts at one arbitrary vertex and continuously grows outward. It adds one new connection at a time to expand a single continuous structure. The algorithm relies on the principle that by consistently choosing the minimum weight bridge connecting the current tree to an unvisited vertex, the final sum of edges will represent the absolute minimum cost. Let's observe this logic in action. We need to construct a road network connecting these 5 isolated villages for the lowest possible budget. Here is our weighted graph, displaying all the potential road connections and their respective construction costs. To execute Prim's algorithm, we must divide our nodes into 2 strict categories: a visited set, which represents our growing tree, and an unvisited set, which contains the nodes we still need to reach. We begin at any node. Let's select vertex A and officially mark it as visited. This establishes our initial boundary. We now scan that boundary for any edges bridging from our visited node into the unvisited territory. From vertex A, we have 3 options, weighing 2, 6, and 3. Applying our greedy logic, we select the absolute smallest edge. That is the path from A to B, at a cost of 2. We add this edge to our tree, mark B as visited, and expand our boundary. Next, we evaluate all edges extending from our newly expanded visited zone, meaning any path coming from either A or B that connects to an unvisited node. The available bridges cost 6, 3, 3, and 8. Once again, we pick the cheapest available option out of all possibilities. We select the path from A to D, costing 3, and mark D as visited. Notice how the algorithm operates blind to the rest of the map. It only evaluates the immediate bridges crossing the boundary from the visited zone into the unvisited zone. Our visited zone now contains A, B, and D. The remaining targets are C and E. We check the edges bridging our current tree to these final unvisited nodes. Look closely at the available paths leading to node C. We could connect directly from A, which costs 6, or we could connect from D, which costs 4. Because Prim's algorithm always takes the immediate lowest cost route, it ignores the expensive A to C path and selects the D to C connection. We add it to the tree and mark C as visited. The only remaining unvisited vertex is E. We scan our boundary one last time to locate all possible bridges. Comparing the options, the path from B to E is the cheapest at a cost of 5. We lock this edge in, mark E as visited, and with all nodes now successfully connected, our boundary dissolves. We have constructed our minimum spanning tree. To verify our total expenditure, we sum the selected edges, 2 plus 3 plus 4 plus 5, giving us a final total cost of 14. You can verify the structural math by checking the edge count. In any valid spanning tree, if you have n vertices, you will always have exactly n-1 edges. With 5 vertices, our final tree correctly utilizes exactly 4 edges. By enforcing a strict, localized boundary check at every step, Prim's algorithm guarantees the absolute minimum network cost without requiring human intuition or global foresight. Now that we understand the visual mechanics, we have to translate this manual deduction into strict mathematical logic so a machine can execute it. We begin mapping the process with a flowchart. The initialization phase is straightforward. Choose a starting vertex and immediately mark it as visited. Next, we enter the core execution loop. Find the smallest edge bridging to an unvisited node. Connect it, mark the new vertex as visited, and check if all vertices are now complete. If not, the loop repeats. In code, this loop is often written as a while statement. The program is instructed to run continuously while the condition all vertices not visited remains true. The critical operation inside this loop relies entirely on an array tracking node status. The code searches specifically for the minimum edge that spans the gap between a node flagged as visited and one flagged as unvisited. This abstract code is simply a formal translation of the localized, greedy boundary checking we just completed by hand. When running this algorithm, there is one major failure condition to avoid. You cannot blindly choose the globally smallest edge on the board if it violates the boundary rule. If an edge connects 2 vertices that have already been visited, adding it will create a closed loop. A spanning tree, by definition, cannot contain cycles. Prim's algorithm naturally avoids this error because its search parameters strictly require one end of the selected edge to land on an unvisited node. For exams, you can memorize the exact sequence with the letters S, V, M, N, R. Start, mark visited, find the minimum edge, connect the new vertex, and repeat. This mathematical theory extends directly into physical infrastructure. When civil engineers plot out municipal water pipelines or telecommunications companies lay down fiber optic cable networks, they use this exact logic to minimize material costs. Understanding the theoretical framework is the first step. Next, we will analyze the time complexity of this process and optimize the code using a min-heap priority queue. Prim's algorithm demonstrates how a series of localized, greedy decisions can be used to construct a globally optimized network.